chapter 8 is a very different chapter from chapter 6 and 7. In chapter 6, we're learning the powerful things that integration can do for us, like find the volumes of a solid or find the surface area of a solid, work, force, pressure, all of those things. And in chapter 7, of course, we learned some new and some old functions, such as exponential and logarithmic functions, but also the hyperbolic functions. So now in chapter 8, what we're going to do is we're going to learn more integration techniques, how to find even more integrals than we've ever been able to do before, past basic approaches to integration and u-substitution. So we're going to learn a bunch of different by hand techniques, almost all of them by hand. There is one that uses a computer. All right, so let's begin with 8.1. And 8.1 really is a review. So this is a review of Calc 1. It's all the techniques that you know and love for doing integrals by hand already. And we just want to kind of refer to those. So we know how to expand the numerator, right? Distribute, FOIL, etc. So for example, if I see this and I want to take the integral of it, it's easier if I just take the integral of 9x squared plus 12x plus 4 with respect to x, all right, which would be 3x to the third plus 6x squared plus 4x plus c. Don't forget your plus c, your constant of integration. No problem. All right, so that's technique number 1. That's expanding the numerator. And you might think, numerator, there was no fraction in this. Well, true, but it is also over 1, but it is a handy technique to use with some fractions. So keep that one in mind. Rational expressions, I should say. All right, now substitution. Oh, okay, we love you substitution. All right, so you might think, wait a second, I know the integral of tangent. You know the integral of secant squared is tangent. But if I want the integral of tangent, that's the integral of sine of x over cosine of x dx. And so then what I can do is I can let u be the denominator, which would be cosine of x. And I would do that because then du, the derivative, is negative sine of x dx. So I actually want negative 1 du, which would just be sine of x. Or if you like, just negative du, either way. All right, so then this is the integral of 1 over u. And then I need a du, but I also need it to be negative. Okay, well, the integral of 1 over something is the natural log of the absolute value of that thing. Don't forget the absolute value symbols. They will become even more important in this chapter. So that's the negative natural log of the absolute value of the cosine of x plus c. And it's just useful for our own purposes to think about how would this have changed if instead of x, it was ax. Well, then when you do u, because this would be sine of ax over cosine of ax dx. U is then the cosine of ax, so then du is negative negative a sine of ax. So I would want negative 1 over a du. Okay, so it's going to be very similar to what we had. It would be the negative 1 over a, because a is a constant, so that would just be sitting out there. And then integral of 1 over u du, which would be the negative 1 over a, and then it'd be the natural log of the absolute value plus c. And then what will happen in here is it would be u, but u would be the cosine of ax. So that's what it would become. I just kind of skipped the middle step in there. I just knew that that was u inside, so I just did it. Not really that much more difficult, right? It's just that instead of negative natural log of cosine of x, it's a negative 1 over a natural log of cosine of ax. But other than that, they're basically the same problem. So that's substitution, the famous u-substitution, right? Lovely. All right, now another technique we have is multiplying by the equivalent of 1 over 1. Very useful for exponentials, fractions, rationalizing, all sorts of good stuff. Okay, so let's say I have this particular one, and what I'm going to do is I'm going to rewrite it, actually. 81 minus x over 9 minus the square root of x, but I'm going to multiply by a special 1 over 1. I'm going to choose the conjugate over the conjugate. In other words, I'm rationalizing. So I'm going to multiply by 9 plus the square root of x over 9 plus the square root of x. And of course, these are already in parentheses because the division sign is a grouping symbol. All right, so then in the numerator, I'm just going to write 81 minus x, 9 plus the square root of x. Like, I'm not sure what to say about that. But then, and don't bother distributing it, you'll see. Because in the denominator, 9 times 9 is 81 minus x. Oh, look at that. That's useful and handy. Right? So we multiply by 1, and we're ending up developing an equivalent expression, which is the integral of 9 plus the square root of x, which of course is the integral of 9 plus x to the 1/2, which would be 9x plus 2/3 x to the 3/2 plus c. So we multiplied by 1 right here, right? We chose the conjugate over itself, the conjugate of the denominator. All right, now how does that help us with secant? Because we don't actually, I'm going to prove that the secant formula works. You know, it just kind of popped out of nowhere by magic in Calc 1. Be like, here's the integral of secant, and then you never know where the heck it comes from. So I'm going to prove that it works. Sorry, I forgot to highlight the multiply by equivalent of 1 over 1. So this is the integral of secant of x dx. And what I'm going to do is I'm going to multiply. Now I can multiply by whatever I want because I can. So I'm going to choose to multiply by something. I'm going to multiply by the secant of x plus the tangent of x over the secant of x plus the tangent of x. And I know it doesn't look like anything, but and why? Well, just because, right? Because it works, that's why. So that's the 1 over 1 I'm choosing. Because I can. I can choose whatever I want. All right, so this would be the integral of, and now think about what you're doing. You're multiplying, and if you'd like, you can put the dx over here. I mean, it doesn't really matter where it goes. But this is secant of x over 1, and it's multiplied by secant of x plus tangent of x over itself. So if you distribute, you'll have secant times secant, which is secant squared of x, plus secant x tangent x. Right, if I distribute that to both of them. And then in the denominator, I have secant of x plus tangent of x. And I know you're thinking, oh, that did not make anything better. Oh, but it did. Because the derivative of secant is secant tangent, and the derivative of tangent is secant squared, which means I have a u substitution. U is the denominator. And then du is the numerator. It's secant x tangent x plus secant squared of x dx, which is all of this. Therefore, what I really have is the integral of 1 over u du, which we happen to know is the natural log of the absolute value of u, plus c, which is the natural log of, and then it was secant x plus tangent x. Plus c. Amazing, isn't it? Now, think of what happened when we did ax before. what was the effect, right? All that happened was that it ended up being that we had 1 over a in front, right? And that's exactly what would happen here. If you did the same problem over with ax, what would happen is the du would be 1 over a, right? Because everything here would be multiplied by a. So we would say 1 over a, natural log of, and it'd be secant of ax plus tangent of ax plus c. That's the only thing that would change, would be the 1 over a in front, and that each of these would be an ax instead of just regular x. It's literally the same formula, but with 1 over a stuck in front. All right, so that was a review of multiplying by the equivalent of 1 over 1.